Our next speaker is Troy Gerwien. His talk is on the limits of my programming language, meaning the limits of my world. Troy is a software engineer with broad industrial experience, and he's currently developing games at VGW. He also maintains and contributes to several open source projects, and is a mentor at Coder Dojo. Troy is interested in what makes software great, not just for the user, but also for the team maintaining it. A big welcome to Troy.
Thanks for that introduction. Thanks everyone for coming. And also, of course, thanks to the sponsors who've made this whole thing possible, and also the volunteers and the organisers. One other thing to remember about DDD is that it's a democracy, and that's a cool thing, right? But you know what the problem is with democracy? Sometimes candidates make promises to get voted in, and then they find that they can't deliver on their promises. So when DDD called for submissions, I was just thinking, like, what would be a cool talk? What would be something interesting to go to? And I just sort of thought of this, there was a phrase that was popping up, and I Googled it and I found, okay, it was this phrase by Wittgenstein, a philosopher. And he said, the limits of my language mean the limits of my world. And I thought, wow, that'd be an interesting thing to think about with programming languages. Like, are we actually stopping ourselves from doing a better job as a software industry because of limits in our programming language, not being able to come up with better solutions or less buggy solutions? So I just shoved one word in there and I thought, okay, that's a nice catchy title. All I need to do now is come up with a pitch, and here's like a little summarised version if you don't remember it. But I'm just saying, like, you know, badly designed programming languages, thought inhibitors, are they part of the reason why we ship projects late and with flaws? So that's as far as I went, unfortunately. I delivered the promise, but I didn't actually stop to think of what it would take to actually fulfil the promise. So when my talk actually got selected, I started to think about what the content would be for this talk, and I thought, oh crap. Anyway, it's too late to change the pitch at that point, and I didn't want to do a bait and switch because there's a lot of depth and a lot of breadth to this topic, it turns out. So I could either just fly over the landscape and not really give much detail anywhere, or I could deep dive into one thing, but then I really feel like I'd be breaking my promise, which was to sort of cover it a bit more broadly. In early feedback, I gave this talk earlier, a draft version of this, and I got some really cool feedback, and someone said, this talk title could be the title of a whole tech conference. You could have a whole tech conference about this, and then people would go to the individual talks and focus on the different areas. And I thought, oh, that's a cool idea. And it actually gave me a way of thinking about what this talk that you've come to would be. This talk would be the keynote. So imagine that we've got a whole day to talk about this topic, and this talk then just means I can just kind of like go at 10,000 metres over the landscape and just maybe point out a few little details here and there, knowing that, you know, that's something that you can follow up in detail in another area. All I can do is really just give it 5 minutes and just cover a whole lot of things. So just at this high level, we're talking about programming languages, and I thought that this is a quote from a really great introductory textbook on functional programming by a couple of guys who are really influential in the ML community and developing Camel in particular. And they said, the programming language we use influences our capacity as programmers to produce correct programs within a reasonable period of time. And something implied in this, we're not talking about, there's no problem with being able to express solutions. We can express solutions. Most of you have probably heard of Turing completeness. It just means if something's Turing complete, you can compute absolutely anything that is computable with that device or that language or whatever it is. And it's actually a surprisingly low bar. Redstone blocks in Minecraft are Turing complete. Excel spreadsheets are Turing complete. I just found out at a previous talk I went to that PowerPoint slides are Turing complete. You could build your line of business application as a deck of PowerPoint slides if you really wanted to. But we don't do that because the two real key things are not can you build it, it's that can you build it in a reasonable period of time and with few enough defects. So these are the two really important things. So just to summarise those two things, I've just used the words convenience and correctness. So these are kind of like the themes that will come back again and again. The pictures, you might be wondering what that's all about. I went to another conference the other day that my work put on, and I just heard this phrase, dragons and rabbit holes, and I thought, hey, that kind of applies. So dragons are like on the edge of the map, there'd be dragons, right? They're the things you want to avoid, the bugs, the undefined behavior in your program. So that's correctness. Rabbit holes is when, in the context of programming languages, it's really difficult to figure out how do I express the problem that I'm trying to solve in the language. The language, maybe it gives you no clear ways to do it and you've got to build up all this stuff yourself, or you're out there searching through half a dozen libraries that give you different trade-offs and so on. So convenience is about what's a reasonable amount of time to be able to come up with a good solution, and how maintainable is that solution. So these are the two sort of overarching themes that we come across. Just to briefly go on those, actually, I think for time I won't go into details, but some of you may have heard of the Sapir-Whorf hypothesis. So convenience is really about this idea that limits in what language what your language can express mean, limits in what you can actually do. So it's language as a thought tool. It can basically multiply your powers, or it could divide your powers. So this is the effort to express requirements as a program using a programming language. So the general thing with convenience is that we seem to be suggesting that we want more flexibility and we want rich language because that's going to make it more convenient. On the other side, correctness, the safety of being able to express things in a program. The set of possible programs that exist out there is huge, right? Probably infinite. Definitely infinite. But a lot of those programs that we could possibly express, they're subtly wrong. They might be almost the right solution, but not quite, but we can still express them. So this sort of implies that we want less expressiveness. We want to basically cut off avenues towards expressing programs that are wrong, that are subtly wrong. For example, some programming languages allow you to express memory management explicitly, but they introduce the dangers because of that, because they allow you to express all the incorrect patterns of memory management as well. On the other hand, you've got languages like Java or C# that have automatic memory management. You cannot express memory management patterns. It doesn't let you do it. It just does it automatically. So it's less expressive, but it's more correct. So if this was a fictional conference, PLConf 22, this would be the billing of the talks. So I'm going to talk just briefly about a bunch of topics here, basically some fundamentals at the beginning. This general theme that I want to bring out, that programming languages are for humans, and then a couple of deep dives at the end. All right, getting started on the first one. Just about motivation. Why would we care about programming language design? Does it really matter in the real world? So Mark Andreessen, about 10 years ago, put out an article that was quite well known, Wall Street Journal, Software is Eating the World, and he was just pointing out how we've just got this unprecedented and growing global dependence on software systems. Just look at the companies that I've listed there, think about how they've transformed our economy. So bookshops, Amazon comes along, the global book industry is now basically a software industry. Uber doesn't have taxis, they don't have their own drivers. They have an app and they have a bunch of software running on the back end, and that's the global company. So more and more of the global economy is actually software. It's built and runs off software. So this also implies that there's these growing and huge risk and reward multipliers because so much of of our economic everyday activity is mediated through software. So if you can increase the convenience of being able to create that software more quickly or more reliably, you might have a great competitive advantage. Equally, if you can improve the correctness because of new patterns in programming languages that just block off avenues of expressing bugs, you might experience less hacks, less exploits, and less failures, which is also going to be good. So I'm not suggesting that programming languages are the only problem for improving our productivity with software. They're probably not even the major factor because we've got people and we've got processes, and that's usually where you look if you want to make things more efficient. But I don't think it's zero. I think that what I'd like to demonstrate today is that programming languages themselves can shift the needle on things that are actually important in the real world. And even if it's a small amount, we're talking a huge numbers here, right? So it's still a huge number. So the question is, what about these numbers? Like, are we doing fine as a software industry or aren't we? So it's not hard to actually just like troll the internet and look for examples, look for studies. I just listed a whole bunch here. I'm not going to go through all of these, but just you can see the general size of the numbers. So the capital T is trillion. There's studies there that are just estimating the cost of software failures in the US alone at something like $2 trillion a year, which is like 10% of the economy. Even if their estimates are way off, even if they're vaguely in the ballpark, we're talking really huge numbers. There's lots of other things there that are easy to find if you're interested. There's also really interesting individual examples, and I'll just highlight this Thorac 25. Back in the 80s, it was a medical device, I believe, for taking x-rays of patients. And injuries and deaths were involved. So that was a combined hardware-software system that they wrote their own software for that system, the company that released it. It had preemptive multitasking. It was basically written in assembly language, and it also had mutable shared state. So the language they were using didn't protect against any of those things. It was all up to the programmers to be able to spot their own errors. And in all their test suites, everything worked fine because they tested it in test conditions, had no problems. Eventually, they actually injured and killed a number of people because certain operators using that machine typed a bit too fast at the wrong time, and that triggered a race condition in their code. And they didn't admit it for a long time because they couldn't reproduce it, but that was definitely an issue that could be resolved with a different choice of programming language. So that's just one example, and there's others there as well. It's also easy to come across articles like this. So Microsoft did an internal study and found that 70% of their security bugs are memory safety issues. And in that article, they particularly highlight that a lot of the software involved is written in C and C++. Memory unsafe languages where one slip up in the developer's memory management code can lead to a slew of memory safety errors that attackers can exploit with dangerous and intrusive consequences. So that's really sheeting home consequences directly to the programming language choice itself. So just to sum up that section, programming language design definitely does have real-world consequences. Okay, another one of these topics that we would fly over in this conference would be that there's never going to be one programming language to rule them all. It'd be nice, right? But, well, here's a picture of each of those little words. It doesn't matter, they're too small to read, but they're all names of programming languages. And the little lines between them basically trace influence, and we're going down the page, so we're back in the 70s up the top, and we're down to a few years ago at the bottom. Anyway, I don't know about you, but I don't really see much sense of convergence in here. And also, it seems like ideas have been around for a long time, and they influence, they go away, they come back. So consensus in programming languages doesn't seem to really be there. So why is that? It's not for lack of trying. So the current candidate for the one programming language to rule them all, in many people's view, is JavaScript. And Atwood even made a law about, well, what he claimed, to be a law, that anything that can be written in JavaScript will eventually be written in JavaScript. And on the far side, on the right-hand side there, it probably too small to read, but it just gives you a glimpse. This is the TC39 committee that decides what things are going to make it into the next version of JavaScript. And pretty much everyone, this is like a third of just what fits on a screen. It goes down, and these are only stage 1 proposals. They also have stage 0, stage 1, 2, 3, and then 4 means it's in the language. So basically, everybody is trying to get the language to do their thing. So, it's not like we don't want there to be one language to rule them all. This is not new. So Tony Hoare, who gave us Quicksort, he also gave us nulls, the billion-dollar mistake. A quote from a paper that he wrote, he says, "We were charged with the standardization of a language to end all languages, designed to meet the needs of all computer applications, both commercial and scientific." And that was in the 1960s in reference to PLI, which most of you, including me, have probably never even seen, let alone worked on. So I guess that didn't work out either. The problem really comes down to the fact that there's competing goals in programming language design. So I'm not going to go through all of these, but just to give you an idea, there's just some I just hammered out. Just to, I think a lot of them would make sense. But I'll give you one illustration. So going back to this example with memory safety, that's relevant here. So some trade-offs here. So for example, if you had a fresh new application you need to develop and you're trying to choose which language to use, if you had absolute real-time performance requirements where you cannot stand garbage collection pauses, let's say. So you're on the side of having to have absolute performance. There is a trade-off there in the sense that you probably wouldn't want to use Java and C# because they do automatic memory management at the cost of some stuttering, some pauses, and just unpredictable performance. So you would probably want to go on the C++ or Rust side because you can actually literally control the memory management in the programming language itself. On the other hand, is there a trade-off, let's say, at the bottom between Java and Rust? So if we choose Rust because it's really safe with memory, why wouldn't we always choose Rust? Well, maybe performance isn't the top thing. Maybe it's just speed of development. And I'm not a super proficient Rust developer, but having looked around, I can see that a lot of people say it's not that straightforward to satisfy the borrow checker. You've got to really understand what you're doing in a non-trivial application. So why would you even put that barrier in front of your team of software developers if absolute real-time performance wasn't an issue? Maybe you're just developing a simple app for your own use, or I don't know, there's lots of situations where you might not have that requirement. So there's a trade-off there. It's harder to get the thing up and running and shipped in Rust than it would be in Java and C#. So it really depends on whether you have that performance requirement or not. So that's just some examples of trade-offs. Okay, moving on. This section would be about essential and accidental complexity. So this concept came from Fred Brooks, who gave us the book, The Mythical Man Month. So back in the 80s, he also wrote this paper called No Silver Bullet. And he gave us this nice way of thinking about software systems as having two kinds of complexity in them, essential complexity and accidental complexity. So essential complexity in software is basically the stuff you can't get rid of because it's the spec. It's like, here's the spec. Please go and implement a program that does this, that does what it says. So if it's in the spec and the spec's complicated, that's essential complexity. If it says you've got to do those 25 things, you've got to do those 25 things. If it says you have to interface with 3 wildly incompatible, terribly written external systems, that's an essential thing because that's what's in the spec, right? So you can't avoid it. Accidental complexity, on the other hand, is stuff that still makes it difficult and complex. They're just basically unhelpful barriers to expressing a working solution, but they're not inherent in the spec. So, for example, manual memory management. If you're thinking about managing your memory, but the spec just says, well, we need this mobile app for the customer, that's accidental complexity. It's just something you have to do on top of solving the essential problem. And choosing different tools can affect how much accidental complexity makes up the overall complexity of your job. So essential complexity sounds like something you can't get rid of. I just wanted to briefly mention that it's not actually true. You can reduce essential complexity, but with another trade-off. So if you think about domain-specific languages or even visual programming languages, they tend to be reduce essential complexity by allowing you to state things at a higher level. You can quickly say how you want things to be done. So for example, SQL for data access. So we don't write Python generally for doing database queries on a relational database. We write SQL and it's really quick and it gets the job done. But it's basically a domain-specific language or a DSL for that one job. So it sacrifices generality, but it means you can do that one job well. So that's great. There's languages that do things. Regex would be another example. There's lots of them. But they don't solve the general problem. It's not like if you're given a brief that you've got to develop a whole app, you go for the specific DSL. There probably isn't one in most cases. You need a general language, so you can't always make this trade-off. On the other hand, accidental complexity. So we still, there's things like boilerplate code. If you're writing your app, if you have to think about managing memory yourself or managing concurrency, managing dependencies, managing versions, these aren't things that are in the spec. They're just things that you've got to get right, and they're just unhelpful barriers that get in your way. Brooks in No Silver Bullet, interestingly, says, we've already solved the accidental complexity problem for the most part. That was his view back in the 1980s. I don't know if any of you can think of what he said was the #1 thing that made the biggest difference in solving accidental complexity. So the thing that made the biggest difference was, in his view, high-level language. So high-level language just means, now, this is something we completely take for granted. When you write program code in any programming language that we use today, pretty much, you are writing code using, for example, English keywords It's human understandable. It's written in a high level. You can kind of see the loops and the conditions in the code. And it's translated down to something that the machine can understand. So that's what we mean by high-level language. It's that the code is independent of the machine that is going to run it. The specific things the machine has to do, they're not represented there in the language. That's high-level language. He estimates that gave us a 5 times productivity boost. So I thought it would be interesting, rather than just, 5 times, what does that mean? We don't really think about it, right? But I'd like us to actually think what it was like for our compatriots, software developers back in the day, before high-level languages, just to give you an idea of how important accidental complexity can actually be. So what were they doing? Well, first example, this is something that I personally remember, because I had a Commodore 64 when I was a kid, and no money. So rather than being able to go and buy all the cool games off the shelf, sometimes we'd come across a magazine and it would say, type the game in yourself. So it just sounds awesome when you're a kid, when you read the description, Space Blaster, this is going to be so awesome, like it's action-packed and everything like that. But then you've got to write this out yourself. And you can see there's a few lines of BASIC at the top, that's bootstrapping, but pretty much the whole game is actually in machine language for the 6502 CPU inside the Commodore 64. And you have to specify it byte by byte as these hex codes. The other thing is, if you get any of those wrong, if you get one letter wrong, one character wrong in any of that, well, if you're lucky, you've probably just screwed up a sprite and it's the colours are mixed up in somewhere. But more likely, most of that will be control flow and logic for the game. And if you just basically change a byte there, all bets are off. You probably crash your machine, lock it up, or who knows, it probably won't be the fun Space Blaster experience you're hoping for. Going back even before that, they had even extra steps. They'd fill out these punched cards. So I won't go too much into that. That's really going back. But I think you get the idea that there was a lot of accidental complexity involved in developing software back then. You've got to think at a really low level. The other thing is there's pretty much no protection from errors, because there's no interpretation step. What you present to the computer, it goes, well, this must be what you meant. I'll just try and execute it. So basically, I like to think of that as a cosmic ray on your punch card just gives you a new program. As far as the computer's concerned, oh, okay, every program that you give me is what I think you meant, and it just executes differently. So a little taste of that. 6502, this was the CPU inside the Commodore 64 and also the Apple II. I've got like 6 bytes of machine code at the top there, and that decompiles into these assembly language instructions. It's just a little loop. It just starts at 255 and it counts down to 0, and then it returns. So that's all it does. What I'm going to do is, on that last byte, I'm just going to change the 60 to a 61. It's 1 bit. It's just changing 1 bit. So watch down the bottom. And now, instead of returning from the instruction, I'm doing some further arithmetic and I'm not returning. And whatever comes after that is what the process is going to keep doing. That's a good example. That's probably just going to lock up your machine. I had to restart my computer a lot of times. Just another example. So now I'm just going to transpose the 2 parts of the 3rd byte. So instead of CA, it's going to be AC. And we can watch down the bottom again. And now I've got pretty much a completely different program. There's now no loop at all, and it also still doesn't return, so you're going to get a vastly different outcome. And I just changed a couple of bits. The program looks the same. So that's all accidental complexity. Just a bonus question to end this section. Can anyone think of any language that we still use very commonly, probably most software developers in this room have used at some point, that has some of these characteristics that I've just been describing? Yeah? Yes, exactly, regex. I like to call it a write-only language. See if you can think of what this regex does. I won't call for volunteers, but I'll just tell you it actually parses or validates email addresses. That's not obvious from looking at it. So the way you would come up with that is you'd think at a high level, okay, what are the parts of an email address? And you translate it down into this kind of almost like machine language. And then if you ever try and want to know what that does again, I would probably just copy it and paste it into one of those websites that sort of decompiles a regex for you and gives you a visualization. It's not that different from what they were doing back in the day. So yeah, we still have this. Okay, moving on again. Now we move into this section where I'm really focusing on the human aspect of programming language design. We don't want to overburden the human. Why is that? Well, I'm just going to start with this quote from Donald Knuth. He's pointing out that programming is the art of telling another human being what one wants the computer to do. Programming languages aren't for the machine, they're for people. If programming languages were for the machine, we'd still be programming in assembly language or machine language, because that's the easiest thing for the machine to process. The reason why we use these high-level languages and then all these very sophisticated tools to translate that down to the machine is that the source code of programs is for us, it's for humans. So if you think about what's scarce in the production of software, it's definitely not making more copies of it. It's free to make more copies of software. Like all the raw materials of what we use, RAM in memory, CPU cycles, like they're really cheap. Right? The marginal cost of that is almost zero. So why is software expensive? And why, we talked before about the trillions of dollars worth of, the cost of software bugs. What makes up the expense? Well, I'd say it's actually human ability. So humans, we've got limited working memory, limited cognitive powers, and limited reliability. This kind of links back to the keynote this morning when we're talking about fallibility of human memory in particular. So that's just one of these things. And programming languages that adapt for that can actually really empower us. Ones that ignore the humanness and we'll see some examples anyway. They're probably the ones where it's going to be harder to express a correct program and increase your rate of bugs. So how could the programming language itself, how could the design of it actually help with this sort of human focus on the programming language, particularly humans being limited? So I've just got a whole bunch of examples there. I just bolded a couple that I could just briefly speak to, like raising the level of abstraction to reduce the semantic gap. So we saw before, literally putting in the hex codes, you can't really look at that and see what the program does. Although I did do an early version of this, and someone who saw the Commodore 64 stuff said, I know what that does, because he had one and he still remembers all the opcodes. But for most of us, if you see source code, you want to see something that is kind of human readable. For most of us in here, that's things like, the English keywords and visual breakdown of blocks in the code. And I put that one there, visuality. Use layout and keywords and punctuation to actually make, we can recognize patterns visually very, very quickly. So if your source code actually allows for that pattern recognition of humans by having visually indented and delimited blocks, we can see that very, very quickly. That works with us. It helps us to produce software faster and with less mistakes. And also, what we really want to optimize in our code is understandability. Not necessarily making source code as short as possible, having a language that is the shortest to express, or the most minimal language, like the one with the fewest constructs. That doesn't necessarily win if it comes at the expense of human understandability. So just one quick example for this section. I'd say most of us are pretty familiar with basic control flow constructs like this. So control flow is basically just, it's an imperative concept for imperative languages, which are the ones I'd say most of us use, like Java, C#, things like that. You do things in order. There's a time-based component. I do step one, then I do step two. And if that's all you could do, step 1, 2, 3, you could only write a linear logic program and it would always terminate depending on how long, just basically how many lines you've got. If you want things that run forever, or run indefinitely, let's say, probably you don't want an infinite loop, you need control flow constructs that can alter the order in which statements are executed. And these really common ones, the top two are loops, so you can keep repeating the same series of instructions while some condition is true, or you could loop over every item in a collection. So they're really common. And then the bottom two are conditionals. So it's like just conditionally execute these things if a certain condition is true, otherwise skip them. Or look at this value and then, depending on what it is, either do this or do this or do this. So that's like a switch statement. Pretty basic, I think we're all familiar with that. But what if I told you we could go even simpler? What if I told you that a single control flow construct could do everything all those others do, and we can just sweep them away and make our language even simpler with just one kind of control flow? Well, it exists. If condition, go to label. So it just means that you should be able to label any line in your code, and then you can say, well, if this condition is true when you execute this line, just jump to that other label. So I thought I'd give a demonstration to show how great this would be. I picked a modern language that actually still allows goto, so I was actually able to test it, and this is working code. So I've started with a prime generator that's pretty straightforward. It basically just goes through all the numbers from 1 to 100, and then for that number, it does an inner loop to try and find something that divides into it, that excludes it from being a prime. So If it gets through that inner loop and it hasn't found any divisors, then it's still a prime, and then we just print it to the console, and that's what it prints out, 1, 2, 3, 5, 7, so on, up to 97. So I just chose that example because it's relatively simple, but it's got loops and it's got conditionals in it. Now I'm going to transform it using my awesome one only control flow construct if condition go-to label. So first of all, I get rid of the outer for loop, and I've replaced that. I needed a couple of labels and a couple of new go-to statements, but it's the same program, still works the same. This is all valid C#. Then I get rid of the inner for loop, then I get rid of the first if, and then I get rid of the second if. And now I've got a final program that does exactly the same thing as the first one, but it's way simpler because it's only got one control flow construct. And also, we got rid of all that weird indenting, and now it's all nice and straight. So there's my before and there's my after. Okay, it's slightly longer. What would you choose in terms of, I mean, we're talking here about limited human cognitive ability, right? Maybe it's just my training, but I would take the one on the left still, even though you could say it's more complex because it's got more different constructs. So it's not about minimality sometimes. It's about working with the human, the way we think. I can visually see the loops in this one. On that one, I would basically have to run it in my head. So if you look for pictures of people doing go-to programming, you often find these screenshots that they've done of some old bit of working out where they'd obviously drawn all over the program source code to try and get it into their head what's actually going on. So on the left, we've just got these. You can express any control flow with these three constructs: sequence, selection, repetition. On the right, you can just use one control flow construct, but it's actually a lot harder to understand. Okay. So that's probably a good segue into this one, which is also about the humanity, the human side of programming languages and how to take it into account. So before we were saying don't overburden the human. Now we're saying don't rely on the human, because even if you make it easy for them, humans are fallible. We make mistakes. So the main point I want to make in this section briefly is that if a programming task could be described as a set of mechanical transforms, then design the programming language itself to just fully automate that. Just take it out of the hands of the human, because we're not that good at perfectly reproducing the same transformation again and again in a manual way. I call this the human compiler anti-pattern. So I don't think you'll find that on Google because I just made it up. But the reason I call it the human compiler anti-pattern, because I'm thinking that, people even get proud of doing this stuff. It's like, wow, I can really reliably create this really complicated code. But actually, what they are doing could be automated by the programming language tools themselves. That's great for this hotshot, whoever they are. That's really awesome for their self-esteem and so on. But statistically speaking, as an industry, it's going to increase our error rates if we require humans to do that sort of stuff. So let's have a quick look at an example that I set up. This is JavaScript. And I've just got a function here that, as it says at the top, it returns the number of files in a given directory. So it's a function. I pass it in a directory path. And at the end, it's going to return me a number, which is how many files, not directories, but files in there. And the way it works is by making a couple of system calls. One is to get a list of all the files in the directory, and it just gives the short names of the files, not the full paths. So then we have to map them to full paths, and then we can go and make another series of system calls, one per file, and get the stats. And the stats will tell us if it's a file or a directory, and then we've got all the information we need to count up the files in the directory. So I think that's pretty straightforward, and I just wanted to highlight that this is an async function, and we use await. I don't want to go into all the ins and outs in that. I'm hoping that enough of you understand a bit about asynchronous programming to just, if you came into JavaScript or another language with async await in the last, say, 5 years, I think that's hopefully fairly easy to understand. But async await is another one of these things that is an innovation that wasn't always around. What came before async await? What was being required of the programmer before it sort of took care of these concurrency patterns for us? Well, when I first started using Node, it was on the 0.x version number. JavaScript, it was always running on JavaScript on V8, but JavaScript at the time didn't have async await. It didn't even have promises. So if you wanted to do asynchronous operations, and Node has always been fully asynchronous from day one, you basically say, go and start this job, like go and get the file stats for me, And when you're done, call this callback that I'm going to give you now. So it's all callback based. It's basically continuation passing. So I've got, the next slide is this exact same program that you would have to write manually. It's the same program. You would have to write this out manually and manage all the callbacks yourself. There's a bunch of them up there. So you ask for a callback, and then you call that callback when you've either got an error. Well, actually, there's all the error pathways. So there's several ways that you could get errors at different points. You've now got to manually do all that bookkeeping. And if you get that wrong, you might just swallow the error, or you might just actually return several errors. Like a basic thing about functions is that if you call it once, it's either going to return or it's going to throw an exception, right? The only exception to that is like an infinite loop, but we won't go into that. Here, you've actually got the erroneous possibilities of calling the callback, which is the equivalent of returning from the function, and sending back multiple errors or multiple returns, or even sending back errors and return values at the same time. There's so many ways that this could go wrong. But people, and I remember coming across Reddit threads with like, it's not that hard, like I'm really good at it, I've never made any mistakes. Yeah, sure. However, this is really just going to, statistically speaking, on average, that's really going to reduce error rates across the board, right? So if the compiler can do it, it should do it for you. That does sort of raise the question of design patterns, because they sort of meet that thing of really mechanical transforms on code to handle certain situations that you can always apply reliably, right? So I'm not saying that they're all bad, but I think it's interesting to look at some of the design patterns, and they're written for specific languages. Some design patterns you really don't need to code in a special way, depending on which language it's in. And it's an interesting framework to look at design patterns that they're not always a great idea. They might actually be telling you that your programming language itself is not expressive enough because you've got to do this sort of manual transformation to get that kind of code to work. That's a talk for another time. So moving on. Making invalid states unrepresentable. Now, this is the section that I would want to do the full talk on, because this is my jam. What I really want to talk about here is type systems. Unfortunately, I've probably got about 5 minutes to cover this section. And to motivate this, like, why would we care about type systems? How does that fit into this whole thing of programming language limitations and so on? Well, this chart kind of says it all. So on this chart, we've got these bars that get bigger to the right. The bigger the bar, the higher the cost to repair a defect in software. And the further to the right you go, it means the later the bug was discovered. So that really tall bar on the right is bugs that were discovered in production. So you've crafted your piece of software, it's gone through all your QA, it's gone out to customers, and at that point, the bug is discovered. If you're lucky, the bug was discovered by your customers, and only hopefully a few of them, and you might have to make them whole, and that might cost some money. If you're unlucky, it might affect all your customers catastrophically with whatever, financial losses. If you're even more unlucky, it's not the customers that are affected, it's you that's affected because someone has found a vulnerability in your code and they've found a way to hack the system and cause all kinds of other damage, like stealing information about your customers. That can be extremely costly. So that's, I think, the sort of rationale for why there's this pattern of raising costs the further out you go. Catching it earlier means catching it in, say, QC. But if you've got, say, a big team of human QC testers, there's a cost involved in having that team, right? So it's quite costly to be using that team. If there's whole classes of bugs that you could find before it even leaves your laptop where you're making the software, it's even cheaper because it never goes through those later steps, right? So this is a time when it's really cheap to catch bugs. The cheapest time is when you just catch things that are wrong in the spec before you even write code. But we're talking about programming languages. So let's assume the spec is correct. What can the programming language do to actually help you catch bugs before they even go out to production, because it's a lot cheaper to catch them there. And that's where type systems come in. By the way, this graph really motivates this concept of shift left. The idea of shift left testing is basically looking at this graph and saying, with all these defects and bugs, we want to shift to the left and catch them way earlier because it saves us a lot of trouble, money and time. So there's a very, very strong link between, most people think of shift left as having better unit tests, but I think there's a really strong link between the idea of shift left, which is great, and static type checking, because type checks are tests. They're tests that you don't have to write as separate unit tests, but they will catch bugs for you before you even run the code. So Good would be that you run some sort of build tool and it tells you, so I'm looking at the top of the screen here, and it says, hey, there's these errors in your code. And you can't take it any further. You can't run that program. You can't release it to production. You can't merge it to main. That's great. Even better would be the middle one, where as you're just typing in your IDE, it's already putting up a red squiggle and saying, hey, this isn't right. So just as you're typing, you're already learning that there's a bug and you fix it straight away. Super easy and cheap. Even better than that is before you've even typed something, it tells you what the options are. So a lot of these powers are actually driven by static type systems. All of this IntelliSense in the bottom, it knows what the valid options are because of the type system that your programming language has built into it most of the time. So these are really powerful things. And type systems are getting really good. So I think most of us are familiar with the old classics, classes, interfaces, and then basic types like numbers and strings and booleans. But if you look out there at all the programming languages that are being developed between research languages, functional languages, there's a lot of languages out there, and there's a lot of types. Some of them are actually not new, like sum and product types have been around for decades in functional languages. Others are, like at the bottom, they're linear types and affine types. Don't even ask me what that last one is. Yeah, they can get pretty tricky, but there's a richness out there now. So if you want to learn about some of those things, like me, putting on a talk where I feel like I should have some sort of authority about it, you can just go to YouTube and start Googling making illegal states unrepresentable, and there's a whole bunch of videos, and they'll often be talking about type system solutions to this problem of, making illegal states unrepresentable basically means the type system should pick up errors straight away if you've specified, I don't know, user first name, middle name, last name. First and last name are required, middle name is optional. If you can say in the type system that intent and you can see it in the code, then you'll catch that error straight away. If nulls are just implicit in all strings, then you can't specify that intent in the code and you can't catch that error until you write a unit test for it or it goes out to production and crashes. So that's what we're really talking about, making illegal states unrepresentable. It's a type system thing, usually. It can go pretty far. So in my wanderings, I came across this video and I thought, oh, there's a typo in the video name. And then I actually started watching the video. By the way, ATS is a research functional language that implements linear types, and they can do amazing things. But the guy says in the first sentence of his talk, he says, by the way, that's not a typo. I actually meant to say a tase of ATS. Like he said, it's so difficult to get right that it's like being tased. So, types, there's a trade-off. Again, there's a trade-off. They can be really super powerful, but they also mean, you might add complexity to the development process along the way. That brings us to Typescript, which is a language I really love. Typescript is basically making a lot of these advanced types go mainstream because they set as a design goal to statically identify constructs that are likely to be errors in code that already existed in massive quantities. JavaScript is already out there. Lots of libraries were already out there. They said, how could we actually analyze code that already exists, that people are already writing with all sorts of patterns, and add this layer over the top of that, a type system. It's a superset of JavaScript that can actually detect where there's errors in the code. There's the low-hanging fruit, like just spotting typos in property names. That's pretty easy, right? But as the project has evolved and matured, they've added some amazing abilities. We're at the point now in TypeScript where it's probably easier to think of the type system as itself a separate programming language. As a programming language, I would describe it as a DSL, or a domain-specific language. It's a language really specifically for checking types, for inferring, checking, and proving that certain type relationships hold. As a language, it's also a purely functional language with no side effects, and it's also Turing complete. So you can actually compute anything that's computable purely at compile time in the type system. So a pro of that is that it really enables you to set up really, really, really specific static checks so you can shift left in all kinds of ways. You can catch a lot of errors before you even run the program, because static checks at the end of the day are things that you can identify just from looking at source code. You don't even have to run it. A downside of type systems that are this rich is that they tend to have some pretty weird syntax that's not familiar to us. And in TypeScript case, it's really interesting because a lot of the types, they actually have the same syntax as the runtime code. It mirrors, but not perfectly. So you've really got to you've got that cognitive load of learning two sets of things, and I think for a lot of people, they don't even recognize the same control flow constructs in the type system as in the runtime system, but they're all there. I just grabbed one quick example off the Typescript blog, and I just modified it a little bit for this talk, but this is basically off their blog, so it's not a super complicated one. But in JavaScript, you might just want to have a simple object watcher, where you could pass in an object with some properties in it, and it will return to you a version of that object that's still got the original properties, but it's got a couple of callback methods that you can attach a callback to, and they'll be called when one of those properties changes. So I've got an example there. If you gave it just an object with an X and a Y in their numbers, it would give you back an object with the X and the Y, but also it's got an X changed method and a Y changed method, and you could put your callback in there and get notified if X changed or Y changed. Super cool. And this is a dynamic language, so it would accept any object you like, and it will set up different properties depending on what those property names were. So we could express the runtime code, and that's what that make watch object does. I haven't put the runtime code there. Like, that's something that most of us could probably figure out. But the bottom part is a type. So we've basically got a type level function here, and we're mapping from the type of the source object, which TypeScript can see, because if you pass in an object there, it can see what properties it's got. And it's going it's basically a function running at the type level. It's going to actually call a few other type level functions to do a calculation of what these new property names are going to be and what their types are, and return that as the output type. So that type is actually used where it says T and, I won't go into the details of that, but it's basically a type level function. So it can do the same computation statically as the program is doing dynamically. So the way that works in practice is that you can say, hey, I want to make a watched object with first name, last name, and age. So if I now go person.on, I realise now that my previous slide had an error in it. The callback that it adds is on, but it's strongly typed for the different strings that you could pass into it. So I want to listen for changes, first name changed, and then you can supply your callback. That's fine, because that's valid. The second two, they're errors, because the first one's saying, well, you can't say first name, it has to be first name changed, and the second one's just a plain old typo. So those are things that before they would have just only been discovered at runtime, and now you can find them at compile time. And not only that, it's not rigid. You don't have to set up separate types for every possible different object. It's like whatever the shape of the object is, it will do a type level function and work out what the shape of this watched object that corresponds to it will be. And this kind of thing, this is a simple example, but with TypeScript, you can go way beyond that. I would love to do a talk on cover more things, like web servers, for example. Finally, has everyone got their popcorn ready? OO versus FP. So if this was a conference, this would be such an interesting and controversial topic. I think that language paradigms, which we haven't really touched on yet, that would be covered here. Language paradigms is the closest thing our industry has to religions. It's very dangerous to, you've got to watch what you say. Fortunately for me, I realised in running through this talk a few times that I wouldn't have time to really do it justice. So, sorry guys, put the popcorn away. I did try, but I really found that in a little 5-minute window, you really couldn't do justice to the debate. So that one, if that's something that you guys are interested in, maybe I'll pitch it for DDD next year. I thought, though, I should at least try and find some good trolling quotes about the two paradigms. The funny thing was, it was super easy to find them for object-oriented, but it was very, very hard. I could basically only find this one sort of meme quote for functional languages. Okay, end note. In a nutshell, the things we're interested in programming language design in ways that it can actually make our lives better and easier and safer is convenience. We want less of these rabbit holes where you get lost trying to find a good solution. We want convenience, that we can express things at a high level in a reasonable amount of time. And the way we do that is by leveling up human capabilities by taking into account human weaknesses. Correctness, we just want to squeeze bugs out of the system by design, make them less possible to even express by shifting left, and in particular with expressive type systems. And I think I pitched that we'd look at things that will emerge in the future. This is a big area where I think there's a lot of work going on in programming language design. And finally, we need to embrace trade-offs. So different languages express some things better than others, and I think it's going to always remain the case that we should choose the best programming language for the job. And that's it. Thank you very much.
Thank you very much, Troy. What an engaging, thought-provoking talk. I think one of the most gripping of today. So thank you. Now we're going to open up the floor for questions. Do we have any questions for Troy? This one over here.
What do you think drives people to be so, some people to be so emotional? Oh, sorry. What do you... Hello?
Maybe it's turned off.
No, it's not on. Can I just yell?
Yep. Try it again.
Hello? Hello?
I can hear you, Nick, so I can repeat your question if you...
That's all right, maybe. Hello? Okay, that's better. What do you think drives some people to be so emotionally attached to a certain paradigm or a certain language, if you've seen it happen?
Well, I think it's like a bit of a minefield even discussing it, because I made an analogy to religion, and there's probably there's a deep analogy there. So I would say sometimes it's you've grown up knowing one thing all your life, and it's very difficult to hear things that say you're wrong. Or even if you came to a certain way of, say, developing software in a certain paradigm yourself, you may have invested a lot in doing it that way, and maybe people with really different views from you just, it's risky to embrace new ideas sometimes because you've invested a lot in what you already know. And typically no idea is perfect, so you can always point flaws in the other people's way of looking at the world.
So a little bit of resistance to change and fear of the unknown.
I think so, yeah.
Thanks.
Any other question?
That's great. Thank you, everyone. Lunch is served out in the foyer. And a big round of applause to Troy.